Okay, here is your final video for Chapter 1, Video 7, I believe, and we're going to wrap up talking about energy. Now, I know I have a few physics people in this class, and I want to make it very clear that I'm not approaching this from a physics standpoint per se. Okay, so I know that there are other ways to describe these things. We're going to stick with what you need to know for this chemistry class, okay? So our first type of energy we want to talk about is kinetic energy, and kinetic energy is a result of motion. So anything that is moving has some amount of kinetic energy. It can be moving very slowly, very fast, and it has to do with its velocity and its mass, okay, as far as how much kinetic energy it has. And we can calculate that from a pretty simple equation. So EK, kinetic energy, is 1/2 mv squared. All right, pretty simple equation. M is mass in kilograms, and this stylized V is velocity in meters per second. Okay, so our units of energy will be kilograms times meters squared over seconds squared. Right? So pretty straightforward little equation. All you need is the mass and the velocity, and you can easily calculate the kinetic energy of an object. Potential energy results from the position or condition I'll just stick with position for now. Position relative to other objects. I said condition, and I'll get to that here in a second. But the idea here, the classic example of potential energy is a roller coaster car sitting at the very top of the first hill before it drops down to the other side. It sort of pauses right there at the top of the hill. And its potential energy is relative to the surface of the Earth. So the higher you go from the surface of the Earth, the more potential energy you have. Now, in terms of condition, that's where we get into where we're concerned in chemistry. In chemistry, the bonds in chemicals, or more specifically, the bonds between atoms, store potential energy. And store is not really the right word, but it sort of makes it's easy to relate to. But they have inherent potential energy in the form of electrostatic energy. Okay, sharing of electrons or transferring of electrons. Electrostatic energy is the potential energy that is held within a molecule. We'll talk about that a little bit later in the semester. But potential energy is a thing in chemistry. So the basic unit of energy, the SI unit, and I mentioned this, I think, in the first video, is the joule. Capital J. And if you'll remember, a joule is a derived unit, which equals 1 kilogram meters squared over seconds squared. Now take a look. Isn't that what we had for our units of kinetic energy? Okay, so we're going to, when we do calculations to find kinetic energy, it's important to be aware of units. Okay, the units must match And in this case, we want the units to match kilograms, meters, and seconds. Okay, if we're talking about joules, there are other units of energy. But if we're talking about joules, we have to be in kilograms, meters, and seconds in order to calculate the potential energy. So let's do an example. And again, I'm going to ask the people that are more versed in physics, especially calculus-based physics, to bear with me on this and don't think about it too hard, okay? So our example problem here, so a 2 kilogram ball is thrown with a velocity of 6 feet per second. What is the kinetic energy of the ball? Right? And in particular, we want the energy in joules. Right? So, like I said, we're taking this very simply. We're not trying to account for the pull of gravity, friction of the air, anything like that. This is a very simple sort of physics problem. Right? But we're taking out all of the real life aspect of it, okay? I suppose you could think about it, a ball being thrown in a vacuum or microgravity in outer space. So let me stop rambling and get back to the problem here, okay? So notice that we have our kilograms, great, but our velocity is in terms of feet per second. And seconds is good. We want kilograms, meters, and seconds. So we need to convert our feet to meters. All right, and so our conversions, we have 1 foot equals 12 inches, and we have 1 inch is 2.54 centimeters, and we have 100 centimeters in 1 meter. All right, so I'm going to do this using conversion factors. So I'm using the same tactic again and again and again, and I'm going to keep saying that. You're going to get really tired of hearing me say it, but it's very important. There's no need to solve things algebraically, I promise you. So I'm going to use a conversion factor that puts feet on the bottom, so 12 inches per foot. So if I stopped here, I would have an answer in inches per second because my feet will cancel out. Now I'm going to put the conversion factor that has inches on the bottom, 2.54 centimeters in 1 inch. So inches will cancel out, so now I have centimeters per second. And I still have the per second. I haven't done anything to cancel that one out yet, so it still exists, it's still there. And my last one, I'm going to say 1 meter is 100 centimeters, which causes the centimeters to go away. So now I finally have the units that I'm after, which are meters per second. So I have 1.82 meters per second. Now I'm going to keep track of my sig figs, right? So each of these things are definitions. So none of them count for our consideration of sig figs. Each of those definitions has what we think of as an infinite number of significant digits. So if they all have infinite sig figs, then the one that matters is this one that has 1 sig fig. Right? So I'm going to keep track because I'm not done with my problem yet. I still need to figure out the energy in joules. So I'm going to track at that first significant digit when I calculate my energy. So our final bit, energy kinetic, equals 1/2 the mass, which was 2 kilograms, times our velocity squared, 1.82 meters per second, tracking that first significant digit. So when we punch that into the calculator, 3.34 kilograms times meters squared over seconds squared. And since we're dealing with 1 sig fig in this part and 1 sig fig in this part, then we should have 1 sig fig here as well. So my final answer should be reported as 3 joules. Right? Because remember, this part right here is a joule. And with that, we are finished with chapter 1. Hopefully this hasn't been too terrible for you to get through. Hopefully the shorter videos are better than the long ones. And we'll see you when we pick up with chapter 2.